Hey again, this is Matt, and in today's video we'll look at taking atmospheric data in order to explore the scientific phenomenon of climate change. In recent news reports we've seen that the Norwegian government has committed to being carbon neutral by the year 2030. They've been prompted and sort of propelled by scientific evidence that climate change is occurring due to the emission of greenhouse gases and carbon dioxide. So what we're going to do today is explore how the climate is changing by taking historic climate data such as temperature and rainfall and trying to model it. So what we do is use historical data measurements of atmospheric temperatures. We're going to try to either support or refute claims of climate change. First, we'll try to fit a sinusoidal function of the form that models the temperature. So one could claim that temperatures are fluctuating naturally. They're just occurring in waves, and we can model this by temperatures. So we'll explore to see whether a sinusoidal function fits our data. We'll also try to fit a linear function of the form that will model our data. And what we want to then do is say, well, which model best fits our data? Or could a possible third or fourth model be better suited to explain the data of temperature and climate change? And ultimately, what we're trying to assess is, do these models support or refute issues of climate change? Before we can model our climate change data with sinusoidal or linear graphs, we first need to collect the data. So we'll use information from the World Bank Group on Climate Change Knowledge Portal. They have data on temperature and rainfall amounts for any given time period. We'll download from 1900 to 2012, and we'll select Norway. So I've gone ahead and I've downloaded this Excel file, and you'll see here that we have the year, we have our temperature in terms of degrees Celsius. I also have rainfall if I wanted to model that data, the month in which it was collected, the country, and then I've programmed in a sine function. And so the sine function here you'll see as a formula is equal to the amplitude times the sine, period times our year, which is our input, plus any horizontal shift, and then finally plus any vertical shift. So this should remind us of the a times sine bx plus c plus d function. And then I also have a linear function that I've programmed in terms of equaling slope times our input plus intercept, so our slope-intercept form. And then I also have a year indicator, so this is if it's 1901, this is 1, 1902 is 2, so it indicates the year in any given decade. And then on this tab, I've defined the amplitude, the period, any horizontal, vertical shift, and slope and intercept, so I can define those and change those in order to get a graph. So here we have a graph, and you'll notice that this graph is very noisy. There's a lot of data in here, so we're not quite sure what to do with it all. Our model doesn't help with all the noise, so we need to eliminate some of this information. Well, first I know that, let's just look at any given decade. Let's just look at 1900, 1910, 1920, all of the years ending in 0. And I can go back to my graph, and this gives me a better sense for what's going on. So I can see that we have some sinusoidal action here for our temperature, and then here's what's predicted based on my model for sine and my linear function. And we'll notice that it's sinusoidal because this is taking every single temperature for all the given months. And so as we know, as the year progresses, the temperatures in Norway change. They fluctuate. So it's not surprising that we get a sinusoidal function. But our model is trying to look at climate change. So as the years are changing, what's happening to our atmospheric temperatures? So instead what I'll do is we want to select a particular month. So I'll take month 6th. Now if we look at all of the data, so now we can see here we have sinusoidal information of our temperatures still. We've reduced some of the noise by looking at just the 6th month out of the year. And we need to refit our data. So here we have our sine function, our linear function, and these are not matching the data. So if we look here, First, let's try to adjust the period. So we notice that there is some fluctuation in general. And it looks like 1, 2, 3, 4, 5, 6, 7, 8, maybe 9. Every 9 years is the period for the change in temperatures. So every 9 years the temperatures are fluctuating. So I can go here and say, well, the period, remember, is 9 divided by 2 pi. That'll actually give me my period. So now we can go back to my graph and, okay, so now I've changed my period. So now every 9 years we're fluctuating. But it looks like I need to do a vertical translation, a vertical shift up to, let's say, 9 degrees, 8. So if we go back to my values, now let's say a vertical shift to 9 degrees. Now the sinusoidal function is a closer match to my data. And I could even now limit the decade again. So we were dealing with just a subset. And that looks like it models it fairly closely. Maybe we need to shift it just a little bit more. So let's try shifting it. If we go to 10, okay, that's a pretty close fit of my sinusoidal graph. So here we have in orange our predicted model, blue is the actual temperatures, and we could try adjusting maybe the amplitude. It looks like maybe it's, well, let's try 0.8. Okay, that's a little bit closer because it's not strictly 1 degree fluctuation. So that's somewhat closer of an evaluation. So we have our amplitude, our period, our horizontal shift. Well, actually it's fairly well shifted to where we need it to be. Now if this peak was occurring over here, then we'd need to shift our data. So we don't need any horizontal shift. I've programmed in the vertical shift. And now let's do our linear model. Well, let's try doing it at shifting it up 10 units as well. If I go back to my graph wall, here we have in gray our shifted line, 10 units up. So now we have 2 models that have been fitted to the data. And we have our sine graph and we have our linear graph. And so now we need to determine, well, which graph is a better fit for the model? Well, that's a tough question. How would we determine which equation is a better fit? How would I determine which one is better predicting the changes in temperature? So it looks like maybe the sinusoidal takes in some of the fluctuations every 9 years, so maybe that's a better fit. But the linear is giving the general progression, so maybe I could change this to be, it's sloping up a little. Okay, so that's, we want to go just a little bit less for our slope. So maybe the linear is. Well, what would it mean if the sinusoidal is correct or the linear is correct? That's a tough question. What do you think? How could we determine which model is a better fit? And how can we be certain of what it's saying? What would it mean that the model is supporting or refuting climate change? How would you go about modeling this data in a way that you could make claims about the changes in temperature to support or refute climate change? Special thanks to the National Science Foundation, Matric, the University of Agder, and the Center for Excellence in Education for helping support and promote these videos.